Hello everyone. Welcome to this next lecture on advanced fluid mechanics. I am Vatsa and I will give the next few lectures. And today we are going to talk about something which is very close to people working in fluid dynamics. The first one will be dimensional analysis and dynamic similarity. And then we will look at some non-dimensional numbers. So the underlying physics behind this dimensional analysis is that the laws of physics or the laws of nature are scale independent. So it doesn't matter whether you are looking at this aeroplane, which is flying in the sky, or if you are looking at a scaled down model in the lab. So this is a scaled down model, so the laws of physics are same. So it is always possible to maintain some dynamic similarity between these two cases, so that the results of of our experiments in the lab can be used directly for designing an aeroplane, for example. So there has to be a dynamic similarity, and this is what we are going to study. So we are going to look into the parameters that will control these kind of flows, and then we will try to come up with numbers. And if we keep these numbers constant between the two cases, we can use the results from the lab, the model experiments in the lab, to the real life situations. And as you can imagine, if you want to test new things, for example, if you want to test new wing designs, it will be probably beneficial for us to do these test experiments and only then implement them in the actual aeroplane. Similarly, if we want to do numerics, so if you want to numerically calculate the drag and things like that for an actual aeroplane, and if you want to do it, let's say if I want to do it on my laptop, it will be very difficult to simulate the full scaled model. So it will be very difficult to simulate something which is as big as as an actual aeroplane, and then I will have to take certain assumptions, and I will probably use a scaled down version of that. And then that's where these non-dimensional numbers and the concept of dynamic similarity will be very useful. So what this analysis does is to reduce the number of variables. So as we will see later on in the lecture, that we can reduce the number of independent parameters that we have in any given process. It can often simplify the governing equations. So the governing equations can be simplified using dimensional analysis, and we will see that in the upcoming few lectures. It can also provide some valuable scale estimates. So and it can help us indicate the most dominant forces that are present in the process. So if of course if the process is done correctly. So we will now look into one of the first and one of the basic examples of such a system. So one of the first examples of using such dynamic similarity could be for a flow through a pipe. So of course we can have different types of pipes. For example, there could be a pipe which is 1 centimeter in diameter and is a few centimeters long. There could be another pipe which is a few meters, let's say 1 meter in diameter. So this is the diameter D, and it could be uh, tens of meters long. So we can have pipe of different dimensions. But of course, the Navier-Stokes equation won't change. There is something which I should mention before we go deeper into the analysis, and that is the laws of physics are scale independent as long as we don't break any underlying fundamental assumption. So of course, if we take a pipe which is 1 nanometer in length, so of course this is not to scale, right? So you have to take my word that this is 1 nanometer. So if we have a pipe which is 1 nanometer in length, then of course the laws of physics are going to change, because We will need to take into account some new forces that we don't have, let's say, in the Navier-Stokes equation. Also, Navier-Stokes equation is a continuum model, right? So we can only talk about cases where the continuum hypothesis is still valid. So of course we can think of different pipes at different scales, and we can try to figure out a dynamic similarity between them. But we should always keep this in mind that this is valid as long as we don't break any underlying fundamental principle. All right. So let's take a pipe, a generic pipe, which has a diameter d, a length L, and there is a fluid flow inside this pipe which is going on with a velocity u. The liquid inside has a viscosity mu and density rho. So what we might want to know is the pressure drop. So there would be a pressure drop. So if this is Pi, P in, and this is P out, then there will be a pressure drop across this pipe. And in principle, we might want to know what is this pressure drop as a function of, let's say, the diameter of the pipe, the length of the pipe, the velocity of fluid inside it, the viscosity, and density. So we can represent this P out by P in by delta P. So we have 1, 2, 3, 4, 5, 6. So we have 6 variables. But if we closely look into these variables, we'll find out that they are all made up of 3 fundamental units. For example, delta P is nothing but Newton per meter square, which can be written as so Newton is kg meter per second per meter square, which is nothing but mass divided by t square length. The diameter, of course, is only has a unit length in it. Length as well only has a unit of length in it. Velocity would be, oops, length per unit time. Viscosity is Pascal second. So Pascal is nothing but Newton per meter square, which is over there. So this would come out to be mass per unit time per unit length. And then we have density, which is nothing but mass per unit length cube. So far, we have just made an inventory of the different variables that we have and the different units that are associated with it. As we know that in this particular problem, we have 3 fundamental units, which are mass, length, and time. So we can choose any 3 repeating variables. So the choice of repeating variables is up to you. So you can choose any three repeating variables as long as they have the 3 fundamental units. And they don't, and also another important thing is that they don't form a dimensionless group. So what does it mean? So it means that we cannot choose, let's say, the velocity, length, and time as our repeating variables, because one, we can always write it as ut upon L, and then this is dimensionless. So I mean the combination of the three repeating variables that we choose should not form a dimensionless unit among themselves. And of course, if we look closely, then out of these 3, we are missing a unit. So we are missing mass. So we don't have a kilogram in any of the 3 units. So of course, we cannot choose anything either of like velocity, time, or length as our repeating variables. So for this particular problem, I'm going to choose the velocity the diameter and density as my repeating variables. So in my tube, for my tube, I'm going to choose the diameter, velocity, and the density as my repeating variables. So then what is left is delta P, the viscosity, and length uh, of the pipe. So then we can form our first dimensionless group. Let's call it pi1. This will be delta P u to the power alpha d to the power beta and rho to the power gamma. So pi has to be dimensionless. And so for u, I have length per unit time. For d, I simply have length. And for gamma, I have mass per unit length cubed. And of course, pressure is nothing but mass per unit length per unit time squared. So now I can equate the dimensions on both sides of these equations. So for L, I will get alpha plus beta minus 3 gamma minus 1 equals 0. For mass, I will get 0 equal to gamma plus 1. And for time, again, I will get 0 equals minus alpha minus 2 equal to 0. So these three equations will give me alpha equal to minus 2, gamma equal to minus 1, and then if I put these two values in equation star over there, then I get beta equal to 0. So basically what I have as pi1 is delta P u minus 2 T0 and rho minus 1. So pi1 is nothing but delta P upon rho u squared. And this is the first dimensionless group that I have. To form the second one, we are going to use L u alpha d beta rho gamma. So again, m0 L0 T0 equals L1 L per unit time to the power alpha L beta and mass per unit length cube gamma. So if we equate mass, then we get 0 equal to gamma. So gamma is 0. If we equate, this was mass. If we equate length, then we get 0 equal to 1 plus alpha plus beta minus 3 gamma. And if we equate time, we get 0 equal to minus alpha minus 3 gamma equals 0. So if gamma is 0, then we get from this equation we get alpha is also 0, which means that beta is minus 1, which gives us the second dimensionless number, which is L divided by D. And this could also be very obvious because if we have length, then the only way to make length dimensionless is to just divide it by the repeating variable length that we have. So for the repeating variable length scale that we have, that was the diameter. So if we just divide the length and diameter, we will obviously get another dimensionless number. So there was no need to do the full mathematics, but we could all, but it's nonetheless good to do it just to be sure. Now we have the last dimensionless number, that is pi3 dimensionless group. That will be mu u alpha d beta rho gamma. So again, we have M0, L0, T0. For this, viscosity will be mass per unit length per unit time. Velocity is just length per unit time again. Diameter is of course length, and density is mass per unit length cube. So here we have 0 equals 1 plus gamma. This is for mass. For length we have 0 equal to minus 1 plus alpha plus beta minus 3 gamma. For time we have 0 equal to minus 1 minus alpha. That's it. So this first equation gives us that gamma is minus 1. The second equation gives us alpha is also minus 1, which means we put these two in star, then we get minus 1 minus 1 plus beta plus 3 equals 0. So this will give me beta is equal to minus 1, which gives me the third dimensionless unit, which is mu upon rho u d. And some of you might recognize this as inverse of Reynolds number. So then the functional equation that we had at the beginning, which is delta P is a function of density of the liquid of the fluid, the speed of the fluid through the pipe, diameter of the pipe, length of the pipe, and viscosity of the pipe. Now this functional relationship can be written as delta P upon rho u square is a function of mu upon rho u d and the aspect ratio L by D, which is nothing but so what this analysis has done is is that it has reduced the number of variables from 5. So here you have 5 different variables which you can tune. So we can tune the density, velocity, diameter, length, and viscosity, right? So from these 5, it has reduced the number of input, the number of control parameters to 2. So if we know the Reynolds number of the flow going through a pipe, and we know its aspect ratio, then we can predict or we can calculate the pressure drop across the pipe. So dimension analysis is a very important aspect for experimentalists because it also allows them or it also allows them to categorize or classify their data. So for example, if we do several experiments and try to plot the pressure drop, the non-dimensional pressure drop as a function of Reynolds number, this all these results would be at an infinite aspect ratio. So we are assuming that the length of the pipe is way bigger than its diameter. So if now we go on and plot the results over here, so what we find is for low Reynolds number, we get an inverse relation with Reynolds. So we get an inverse relation between pressure drop and the Reynolds number. In the intermediate range, we actually get an increase. And then for smooth pipes, we expect that the pressure drop will decrease as Reynolds number go to infinity. However, this is not quite we see in real life. So in real life, we find that in the later stages, this pressure drop actually goes to a constant value. And it was only in 1933 that Johann Nikuradse, who was a PhD student of Ludwig Prandtl, so Johann found out that this reason why this pressure drop goes to a constant value at high Reynolds number is because of the roughness in pipes. So if we denote this by E, then what he find out was that at different values of E, we can have different constant values of this pressure drop as a function of Reynolds. So then we can define another non-dimensional group which will have the roughness E. So E is the roughness, U is again the velocity, D is the diameter, and rho is the density. Once again, we can do this exercise. And what we will find indeed is that pi 4 is nothing but E upon D. So coming back to this graph, what Johanna found out is that at different values of E over D, we can have different constant values of pressure drop as Reynolds goes to infinity. So of course we can write in the final form we can write that this pressure drop across the pipe is a function of inverse Reynolds number, the aspect ratio of the pipe, and the roughness characteristic of the pipe. So now we can look at a different example. And this example is drag on sphere. So imagine if we have a sphere in an external flow of velocity u of a liquid which has a density rho and viscosity mu, and the sphere has a diameter given by d. So the drag force, so capital D is the drag force experienced by the sphere will be a function of the density of the liquid, the velocity of the free stream, of course the diameter of the sphere, and the viscosity of the fluid around. Of course, there could be a roughness factor, so the sphere surface could also be rough, but we are going to assume that the sphere is smooth. So we will only talk about a smooth sphere. So if we redo all the calculations that we did for the previous case by using the repeating variables as density, velocity, and diameter. So if we redo our calculations, then what we will end up getting is that the drag divided by rho u square d square is a function of Reynolds, which is rho u d by mu. So I'm going to leave this as an assignment. So I want you to start from here and then reach this functional equation, which means that we can go on and plot this as a graph where we have d upon rho u square a on the y-axis and Reynolds number on the x-axis. This a is nothing but the projected area of the sphere. But before we plot the experimental results and try to see what happens, let us think about the problem a bit more. So another way in which dimensional analysis can help us is to identify the forces, the dominant forces in the system. So let us think what it means when we say that Reynolds number goes to 0, or then when we talk about a Reynolds number which is way smaller than 1. So what it means is that the viscosity dominates. So the viscosity or the viscous stresses are the most dominant force in the system, which means that the drag will be a function of velocity, diameter of the liquid, and viscosity. So another way of saying that Reynolds number goes to 0 is to say that the density of the liquid goes to 0. So in that limit, we find that this drag force is similar to ud mu. So if you compare the dimensions, you will find out that both have the dimension of Newton. And then if we divide d upon rho u square a, what we end up getting is this relation, that the drag coefficient is proportional to 1 upon Reynolds. So for Reynolds goes to 0, we expect a behavior like that. Now, for the other limit, when Reynolds number is way higher than 1, then it is inertia dominated. So inertia of the liquid dominates, which basically means that the drag force is now a function of rho u and d, uh, small d. So no viscosity. So viscosity is almost 0. And in that case, we get rho upon d upon rho u square a as constant. So at high Reynolds number, we expect a behavior which looks like that. And now if we go on and look at some experimental data, then indeed, this is what we find, that at low Reynolds number, so in the viscous limit, the drag reduces, and asymptotically as Reynolds goes to 0, it follows a 1 upon Reynolds behavior. And then if in over here at high Reynolds number, we get a constant value of the drag coefficient. And later on, as the Reynolds number is increased even further, we get a non-linear, or we get a different behavior, and that is because of the onset of turbulence. So we won't talk about that. But indeed, as you can see, that just by doing some dimension analysis and some force estimations, we can find these two limits. So we can find this limit of where drag coefficient goes as 1 upon Reynolds, and the other one where the drag coefficient is basically a constant. So let us look into another case. Imagine that there is an orifice, so there is a small gap over there, over here, from which a bubble is going to come out. So let's see what happens. This red part is the bubble. This bubble will grow, and it will keep on growing, and at some point there will be a pinch off. So what are the relevant forces in a system like this? So what we saw in the video was an orifice and a bubble coming out of this orifice, and at some certain diameter d, this bubble took off. Can we predict this diameter? So to predict the diameter, we need to know the relevant forces in the system. So the most relevant force, I mean, one which you can easily recognize is the buoyancy. And then of course there's surface tension force. And these two are the competing forces in the system. So we can imagine that the force of buoyancy would not be nothing but delta rho, which is a difference in the densities of the liquid and the gas, times acceleration due to gravity, and the volume, which would be a function of d cube. And the surface tension force would be sigma times d. So sigma is the surface tension coefficient, which is Newton per meter, and d is the diameter of the drop of the bubble, which is basically in meters. So if we relate these two, so if we say that the force of buoyancy is proportional to the force of surface tension, so that's the capillary force which is holding the liquid back. If these two forces are comparable, then we can write this. Then this will give us that d square is nothing but sigma upon delta rho g, and then d is square root of sigma upon delta rho g. And this diameter or this radius is commonly referred to as the Fritz radius, the Fritz diameter in fluid mechanics. So indeed, this gives you an idea about the strength of dimensional analysis, where just by looking at the relevant forces in the system, we were able to predict we were able to give you an estimate about the Fitz radius. Of course, in reality, things will not be this ideal, And we will also have to account for the contact angle at the orifice between the liquid and the substrate, and also other things such as the roughness of the substrate, etc. Now, let us look into some significant non-dimensional numbers in fluid mechanics. So the first one would be Reynolds number. We have been talking about this number quite a lot. It's given by rho u d by mu. Then what this number signifies is basically a comparison between the inertial forces and the viscous forces. So if Reynolds number is way smaller than 1, then the viscous forces win. And then this leads to some specific cases such as the Stokes flow, a creeping flow, etc. And if Reynolds number is way bigger than 1, then we get a turbulent flow. Another important number would be the Froude number, which is nothing but a comparison between inertia and gravity. So depending on who you ask, you either get u square by gd as your Froude number or u upon square root gd. So both of them are valid. It's just a factor of square root which is different. And then the third, another important number is the Mach number, which relates the flow, the flow velocity in the system as compared to the speed of sound. Of course, as you might have learned in your undergrad classes, is that if this Mach number is way smaller than 0.3, then we know that the flow is incompressible. Whereas if this Mach number is way bigger than 0.3, then we cannot neglect the compressibility in the flow. There are other numbers, such as we can also define an Ohnesorg number, which is given as this. So this number is mainly used in cases where you have bubbles or droplets. So there, mu is the viscosity of the liquid, rho is its density, sigma is the surface tension coefficient, and r is the length scale. In case of droplets and bubbles, this is the radius of the said drop or bubble. And this one is nothing but a comparison between the viscous forces and the surface tension forces. Similarly, if we remember the case of bubble pinch off from an orifice, then we found out that this diameter d of the orifice was proportional to sigma upon delta rho times g. So if we divide the two sides and then square it, so basically if we bring out something like this, then this also is dimensionless. And this particular number is called either a bond number or an Edwards number. So again, depending on who you ask, you can get different answers to the name. But what it does is that if this bond number is way bigger than 1, then we have a case which is gravity dominated, so gravity or buoyancy dominated. And if this bond number is way smaller than 1, then we have a case which is dominated by surface tension. In fact, another place where this bond number is relevant is immediately after a rainfall. So immediately after rainfall, you might see a picture like this, where you can identify some really tiny droplets. So this one, maybe this one, or even these. And you can see that the shape of these droplets are either spherical. So it's spherical. So it could either be a sphere or it could be a spherical cap. For example, this the shape of this drop can be approximated by a spherical cap. Same for this one or these ones. However, If you look at really big droplets, for example, this fat guy over here, and there you can see that this is not a spherical cap. In fact, this is something which we call a puddle. So what is the difference between a puddle and a spherical cap? A droplet, well, basically, you can see that if the drop sizes are small, so if they are smaller than a critical size, then we see them as a spherical cap. However, if the size the size increases, then we see it as a puddle. In fact, if we calculate the bond number, so bond number, which is given by delta rho g r square by sigma, then these guys, so the one which shows a spherical cap, have a bond number which is much smaller than 1, whereas in case of puddle, we have a bond number which is greater than is much greater than 1. So puddle is a case where gravity wins. So if the gravity wins, then it will flatten the droplet. So if we have a drop sitting on a substrate and the gravity wins, then we get a case like that. So this is the case where gravity will win. Whereas if we have a case where surface tension wins, then we will have a spherical cap. So this is another place where you can see that there is a difference in scale depending on which forces dominate, and clearly we can you can identify the relevance and importance of dimensionless numbers in these cases.